MOSFET structure figure shows a simplified structure of an NMOS of an N-type NMOS device fabricated on a P-type substrate, also called the bulk of or the body. The device consists of two heavily doped N regions forming the source and drain terminals. A heavily doped conductive piece. Here you can see the figure structure of a MOS device of polysilicon, often simply called poly, operating as the gate, and a thin layer of silicon dioxide SiO2 insulating the gate from the substrate. The useful action of the device occurs in the substrate region under the gate oxide. Note that the structure is symmetric with respect to S and D. The dimension of the gate along the source drain path is called the length L, and that perpendicular to the length is called the width W. Since during fabrication the SD junctions side diffuse, the actual distance between the source and the drain is slightly less than L. To avoid confusion, we write L efficient is equal to L drawn minus 2LD, where L efficient is the effective length, L drawn is the total length square, and LD is the amount of side diffusion. As well as we see later, L efficient and the gate oxide thickness Tox play an important role in the performance of MOS circuits. Subsequently, the principal thrust in MOS technology developed is to reduce both of these dimensions from one generation to the next without degrading other parameters of the device. Typical values at the time of this writing are L efficient similar to 0.15 nm and Tox similar to 50 ohm. In the remainder of this book, we denote the effective length by L. If the MOS structure is symmetric, why do we call one N region the source and the other the drain? This becomes clear if the source is defined as the terminal that provides the charge carriers, electrons in the case of NMOS devices, and the drain as the terminal that collects them. As the voltages at the three terminals of the device vary, the source and the drain may exchange roles. These concepts are practiced in the problems at the end of the chapter. We have thus far ignored the substrate on which the device is fabricated. In reality, substrate potential greatly influences the device characteristics. That is, the MOSFET is a four-terminal device. Since in typical MOS operation the SD junction diodes must be reverse biased, we assume the substrate of NMOS transistors is connected to the most negative supply in the system. For example, if a circuit operates between 0 and 3 volts, V sub NMOS is equal to 0. The actual connection is usually provided through an ohmic P plus region as depicted in the side view of the device in figure. Here you can see the figure substrate connection. In complementary MOS CMOS technologies, both NMOS and PMOS transistors are available from a simplistic viewpoint. The PMOS device is obtained by neglecting all of polysilicon is silicon in amorphous non-crystal form as explained in chapter 17. When the gate silicon is grown on top of the oxide, it cannot form a crystal. The subscript drawn is used because this is the dimension that we draw in the layout of the transistor. Section 2.4.1. Here you can see the figure. A simple PMOS device, B PMOS inside an anvil. The doping types including the substrate, figure A, but in practice NMOS and PMOS devices must be fabricated on the same wafer, that is same substrate. For this reason, one device type can be placed in a local substrate usually called a well. In most of today's CMOS processes, the PMOS device is fabricated in an anvil. Figure B. Note that the anvil must be connected to a potential that such that the SD junction diodes of the PMOS transistor remain reverse bias under all conditions. In most circuits, the anvil is tied to the most positive supply voltage. For the sake of brevity, we sometimes call NMOS and PMOS devices NFTs and PFTs respectively. Figure B indicates an intersecting difference between NMOS and PMOS transistors. While all NFTs share the same substrate, each PFT can have an independent anvil. This flexibility of PFTs is exploited in some analog circuits. Thank you.